love to say hi, everyone. Thank you so much for being here today for the OAR 2025 Outstanding Scientific Paper Library Seminar Series. My name is Katie Poser. I'm the Outreach Librarian for the NOAA Library, and I am truly delighted to introduce the authors of this year's winning papers. The OSP, or the Outstanding Scientific Paper Award, is a program established by OAR to celebrate the incredible science that OAR employees and affiliates are producing. After all, the heart of any great research organization is the quality of its publications. This award is our way of celebrating authors who do just that. They produce brilliant work that advances OAR and NOAA's mission and stands up to the rigorous independent scrutiny of peer review. While these authors received formal recognition this past summer, we wanted to create a more informal space for them to share their work in more detail. Today's seminar is a fantastic opportunity to hear directly from them and to dive into their research together as we see firsthand the significant impact their papers have had on OAR and NOAA as a whole. And today is our last seminar in the series. It is going to be The Warn on Forecast System from Vision to Reality by Dr. Pam Heinselman. She's with the NOAA National Severe Storms Laboratory, and she is the Deputy Director out there of Deputy Director for Science. Let me get that right. Okay, I'm going to turn it on over to Pam.
Thank you. Thank you. And thank you so much for that introduction. It's very much appreciated. And I am going to turn off my camera so we can focus on the slides. So let's go ahead and get this started. So first, in recognition of this being very much a group effort to develop the system, Warn on Forecast.
Pam, I'm going to stop you 1 second. I am not seeing your slides, so I want to make sure those come through.
Okay. Oh, do I need to do the screen share again?
I think you do.
Okay. Excellent.
Perfect.
Okay. All right. So first, I wanted to start by recognizing all the authors on this associated with this award. And there's also a picture of the number of them here. And so it's really taken a village to get this work moving forward and to where we are today, not only with our federal scientists at the lab, but with our scientists at the University of Oklahoma, and work with the Global Systems Laboratory as well. So why Warn on Forecast? What was the whole motivation behind what I'm going to talk about today? Well, it's really driven by a societal need. So we know when a tornado is approaching or signals are starting to be shown on a weather radar, the lead time that can be provided, there's a limitation to that. And of course, warnings are really imperative to people being able to take shelter. They're short, they're binary, and as I said, very effective for quick response to protective actions. But we also know that in some communities, for mobile home communities, for example, people who are out at outdoor events, our families may require more lead time and information to take protective actions. So the vision then was to be able to, instead of warn on detection, to be able to warn on forecast, hence the name Warn on Forecast. So the idea was that perhaps when a storm is first forming, as you can see in the visualization, we'd be able to input data into a data assimilation system, run out the model, and to be able to produce a swath area of impacts, the timing of those impacts, and also the location of those impacts. And so vision from a storm forming, seeing a swath there of where a tornado may occur with probabilities associated with it, and then verification looking like something stellar on the other side of this graphic. And this vision was output in a paper by David Stensrud et al. In 2009. So what would it take to achieve a vision like this? So there were a number of different things. For one, at the time, producing targeted probabilistic forecasts for individual severe storms was not something that was available. Data assimilation was not particularly rapid. We knew we'd have to be bringing in radar data, satellite data, et cetera, as soon as we could to keep updating the starting point for forecasts. We also knew that all our visuals and the system itself was going to have to be able to run very fast paced if it was going to eventually be used in operations. And then, of course, it was very important for us to produce visuals and things like that that could be very, very helpful for forecasters if we achieved being able to do the science in the first place. So, what we ended up designing was the Warn on Forecast system, and this is a complicated graphic showing all the different pieces for those of you who may be interested in those details. But essentially, what we did was what we do with this system is we have a domain that's run that covers a couple states. So the idea is that these domains would be run where the greatest threat is for weather, whether it's tornado or flash floods or severe storms, for example. And then we built this system so that it brings in observations from GOES-R. You can see some different observations there. Weather radar with the focus of using the multi-radar, multi-sensor data, and then also bringing in surface observations. So we then get an analysis that forms the baseline, also using initial conditions and boundary conditions as indicated over here. We run out 36 members, and then from those members, you can see we generate forecasts with 18 of those members, and those forecasts get generated every 3 and at the top and bottom of the hour at 3 and 6 hour timeframes. And this assimilation system is running every 15 minutes. So we're always bringing in the most recent data so that when we launch another forecast, it's based on the best possible initial conditions. So that's the design. And if you are curious to say, well, how does this compare with the HER that's been operational for quite a long time? Well, our system has a lot of its basis in the HER itself. So it's been a great collaboration with GSL to make this happen. The areas where we've done our own innovations are in these check boxes where you don't see them with the HER, and you also see that we applied a different type of microphysics scheme, and then of course the focus on the really rapid data assimilation and output from that. So what we've developed then in whole is a cloud-based system. We first started on HPC. We now have a end-to-end cloud-based system, runs in terms of targeting regions like you see here, 2 different domains running at the same time for different types of weather events. And the system, if you want to go back and see some of the various events that we've run before and that we still show some in real time, this is the link for that. So once we had this system developed, then of course, the next question, as I said in my earlier remarks, was how useful might this be for end users? And so starting in 2017, we worked with the Weather Prediction Center. We worked with the Norman office, which is local for us here in Norman, Oklahoma, is where the National Severe Storms Laboratory is located. And then we expanded from that to also work with the Southern Region WFOs, with the Storm Prediction Center, and we've also worked with the Aviation Weather Center. So started bringing people into our test bed and also testing these products experimentally in real time. And so this work was really critical to making sure that we could iterate on this system and make it useful for forecasters. So at the beginning of that time frame in 2017, one of the first big events that we had interaction with the Weather Service using our data in real time was on the 16th of May, 2017. And so here in this diagram, you'll see two different swaths showing the probability essentially of rotation associated with storms. And then you'll see the actual tornado events associated with them in these lines, so showing the track. And then you can see in this first case, Warn on Forecast was used by the Norman office essentially to provide a warning of a warning, right? So they were giving a prediction that a severe weather was very likely and that tornado warnings would likely be issued. And this information went out to EMs in the area and enabled them to get themselves in place early on. So another group I mentioned, the Weather Prediction Center, they're very much focused on the water, right? Are we going to have heavy rainfall events? So in this case, I'm showing a number of different products that they had available to look at them. And so in the bottom here, you're seeing different thresholds of the probability of precipitation. This one for this particular event was greater than 5 inches, probability greater than 2 inches. And then we're also seeing the actual accumulated rainfall here from multi-radar, multi-sensor, and then the 50th percentile accumulated rainfall from our actual Warn on Forecast system. And so you can see in this graphic, this is the forecast that was put out using these data in their real-time operations. Okay, and next, Warn on Forecast has also been used as a hail forecasting tool. And so in this case, the Storm Prediction Center and the local office were looking at these images. Here you are seeing the ensemble probability for the 90th percentile from the ensemble, and other images, and then you can see that they put out a graphic indicating a high probability of significant hail associated with that, and then one also by the Weather Service. Okay. So what we saw through this iteration, and that's just a couple examples that were shown in our publication at the time, was that Warn on Forecast could be used by the Weather Prediction Center and the Storm Prediction Center to kind of get a bigger picture initially at the watch scale in terms of what might be happening in the 3 hours prior to significant events. So this is a 3-hour lead time forecast with, again, rotating storms. And then here we're 90 minutes out, so you're starting to see a little bit of honing in by the ensemble system as we're getting closer to the event. And then finally at a 30-minute lead time, focused even more so on the individual storms as to what actually happened. So filling in a critical gap where no other models were providing this type of updated information between the watch and warning scale. So in terms of the skill, you might be wondering, is like, well, how does that skill, what does it look like? And what really is the dependency on the data assimilation? So what I'm showing here is a time frame from 1 hour out to 3-hour forecasts, and then the probability of forecasting the storm in the right place and time. And so you can see here with the blue line, when a storm is new, it's just starting to initiate, there's not a lot of history there with the weather radar data. So the probability is, it's still decent, But as we get on in time with the storm having existed for a longer period of time, you're going to evolve into a much higher probability of getting the storm at the right place in time, which goes, again to the graphic where we were talking about the watch scale, where there's kind of an initial idea, like you see in this indication here, Chicago, we had a lower, a broader and perhaps lower indication of probability of severe storm here, and then early initiation, it's becoming a little bit more defined, and then here it's mature, and you see a very clear and more concise picture of what the threat looks like. Okay. So you might remember the graphic that I showed you initially was from Stensrud et al. 2009, and it showed an initial storm and then a swath with time frames showing where a tornado might occur. So as we wrapped up the publication that we've been talking about, I said, okay, let's look to see if we've done anything as specific as that original graphic that we were envisioning what Warn-On forecast could do. And so this is an actual forecast from the system where you see, initially there's a storm here, the model took that information in, we're able to project a probability swath here for severe weather. And this is showing the storm as it evolved, and then the location of actual tornadoes that were associated with this event. So at the beginning, I talked about a number of challenges that were associated with the development of this system. And so now we have checked off all of those check boxes, and the Weather Service, a number of the Weather Service offices are using this to project probabilistic swaths forward, some of them even building tools to take this information and have a first guess graphic that can be issued, like the example shown here. I wanted to show also, just a little bit of a broader spectrum of the types of events that we've run on. So I've talked, a bit about tornadoes and, not only figuring out where the location might be, but making sure we're getting the environment right. And so that's what this image is showing here is I think it's the cape that's associated with this specific event. We've run for a number of damaging wind events. This is an example of one in Arizona. So we are not Oklahoma centric. This is run across the whole United States. A derecho event, getting the location and mode correct for that. So in the black is the actual weather radar data from the MRMS, and the other part is our forecast. A number of flash flooding, able to hone in on the locations for those, as well as severe wind events on the East Coast, and a significant hail-producing storm here shown from Texas. So earlier I showed this graphic with the evolution of the work that we've done in working with users. And so where we are today is that the National Weather Service has stood up this system so that they are running this end-to-end system in operations as a part of the Office of Science and Technology. And so we are so excited about that. And what that means is that the Weather Service, is now running completely. They are deciding where to place the domain, and forecasters across the country, then when the domain is running in their area, have the opportunity to look at it, and they're providing feedback. And so this is one of the more recent success stories where Warn-On forecast was showing the probability of severe winds between 3 to 5 hours ahead of time. You can see that really intense probability developed between Tucson and Phoenix. And so the Weather Service office put out this graphic indicating impact of blowing dust associated with this particular event, with 90 minutes essentially ahead of that event impacting people in that area. We've also had this past year a number of really significant events. This is the outbreak on March 14th, and here we're showing the particular tracks for tornadoes that happened along with the predicted rotation strength from Warn on Forecast. And this is another example where the National Weather Service acted on the very strong confidence shown by WoFS. And importantly, they shared this information with EMs, and that information was, an EM was able to use that information to tell his constituents in a rural area to take shelter. And at least 125 people showed up at that tornado shelter an hour before an EF3 tornado arrived. So this is an example where we're really starting to see the end-to-end from this system running. It's used in Weather Service, emergency managers getting hold of that information, and then being able to take action to protect the public. And another thing that we have been doing is really plugging in after some of these events and finding out not only from the forecast office, but the EMs, exactly what they were doing and what their confidence was in the outcomes. And so here are just a couple quotes. Here's one from an EM. In 30 years, I've been a meteorologist. I've never done this, but I have to give you the highest alert that I could give you, and it's still hard to talk about. So they gave their constituency that long time alert, and we're able to get people to a safe place. All right, so that kind of wraps up kind of where we are in this exciting transition to the Weather Service. But in the paper, we also talked about our next goals with the Warn on Forecast system. And so I just want to touch on those briefly before I wrap up. So one of those is developing a Warn on Forecast system with 1 kilometer grid spacing. So that work has been going on by part of the team for the last several years. And so this is just one example from that work where you can see a 3 kilometer WASP, which is the grid spacing that I've been showing you with the system, and then the 1 kilometer. And so from this particular event shown from 31 March 2023, you can see much more specificity in the location and intensity compared to the actual tornadoes that happened with that event. One of the challenges with running this in real time is that it takes a lot of compute to do that. And it also has to be able to, a lot of compute to run fast enough. And so this isn't in a place where it could run in real time on a regular basis. It's exciting to see the impact. Another thing we've been working on is WoFScast, which is essentially an individual, focusing graphcast that was developed in industry on Warn on Forecast. And so there's a nice paper out on this by Flora and Potvin 2024. And so the goal here has been to see if we can use AI technology to emulate the system that we've been talking about. And so this is one example in terms of the reflectivity being produced by the system. This is the regular Warn on Forecast. This is from WoFScast. And of course, we care about the underlying representation of storms. So is the emulator getting the storm in the right place for the right reason? So we do things like looking at cold pull information, as we can see here, to see how the physical model representation from AI is comparing to the actual model representation. And so that is looking very encouraging. And as is common with AI emulation, it's able to deliver the forecasts a lot faster. And so we may be able to use this to design a 1 kilometer version of an AI WoFS system eventually, because it will be able to run faster, perhaps increase the size of our ensembles, and even run over a larger domain. One other thing, and there we go. One other thing that we worked on actually early in the WoFS evaluation with forecasters was looking at its use for a forcing function for FLASH, which if you're in the Weather Service, you've probably heard of FLASH. If not, it stands for Flooded Locations and Simulated Photographs. So taking that water and then routing it. So this is an example of the normal QPE forcing, where you're taking QPE estimated from multi-radar, multi-sensor. And so then you get this swath of area of concern. However, when you force that model with warn-on forecast, you're going to get a forecast, right? So then you can see the outcome from that addition of WoFS. And this is something that we showed forecasters in the testbed environment. And we saw some impact from that in terms of the potential flash flood lead time. So now we are looking at strong potential for some funding to actually move this forward. So we've been doing some testing with this. This is just one example from the recent tragic event in Texas in Kerr County. And so this is showing a photograph that was forced by warn-on forecast. This was the start. This is the current time. So this delta here is showing you how much time you would actually have prior to the first warning that was issued, first flash flood warning, second. And so this dark black line is showing the actual estimated from MRMS. And then the blue lines are showing the outcomes from the WoFS ensemble. So we are really intently going to be working on this, because we're just so focused on wanting to produce an output, a new tool like this that could be used in situations like that devastating flood. And then finally, the unified forecast system is the pathway to operations. And one of the things that we've been working on, again, with our CRO partners, with the Global Systems Laboratory and NCAR, is to take our current version of warn-on forecast, which was developed on the community WRF built model, and move that into the community MPAS model. So we are in the process of doing that, and RFS is in a similar place. So we're working on that jointly. And this is just one example of an event that was forecast by WoFS, and working on moving into MPAS, where we can actually see some improvement in some cases. And so this is a big focus for us. We had a testbed and JTTI proposal funded to be able to work on this collaboratively and move it forward, with the potential for the MPAS version of WoFS to become operational in FY29. Okay, so to wrap up, where are we right now? So we are in this transition phase where the WoFS is being demonstrated by the National Weather Service. We're looking at MPAS WoFS by 2029. It's possible that Warn on Forecast may become operational officially somewhere in here with V1, which would be the WARS version, and V2 may be the MPAS version. And then we will be continuing work on the 1 kilometer WAFs and WAFs cast. So you can see that work down here. And so with that, I yield the floor and look forward to responding to your questions.
Awesome. Thank you so much, Pam. Okay, we're going to move to our Q&A, and I'm going to ask Pam to come back on screen. Okay. Awesome. Excuse me. Got a frog in the throat. We have our very first question, so I'm going to put that on the screen so everyone can read it. With the AI-based models, would you also be able to assimilate data more often? Radar and satellite data is available much more often than the current 15-minute assimilation. Would that give even better results?
Yeah, that's a good question. So with our current system, we're actually able to bring in data more frequently. We've done testing with phased array radar data, for example, which can come in as frequent as every 1 minute. And so it's possible with our existing system and would be possible with an AI system as well. And I think, the potential that we've seen there is really for the initiation, so like the rapid growth of storms and then also the dissipation of system. That's where you really get the benefit of having even more rapid DA.
Okay, thanks, Pam. I'm not seeing another question, but I have one myself. So, what from the unexpert side, how are you deciding, or who is deciding the how much lead time is best to give for different events?
Yeah, that is a really good question. So I'm glad you opened the floor for that one. So one of the things that I want to make clear is that we've learned through some social science studies as well as working with the Weather Service is that warnings are still critical. So we are not, looking, and neither is the Weather Service, to remove warnings. So those are still important, and they usually go out about 30 minutes to maybe 45 minutes. And so what Warn on Forecast is looking at is really providing the lead, what we're calling effective lead time, so not warning lead time, but really preparatory lead time prior to the warning being issued. And so the time that's needed there, it really depends on the audience that we're talking about. So, if you're talking about people, in a nursing home or a hospital, they might need a couple hours to be able to move people to a safe place. Or, with EMs, they're able to make decisions and, get situated where they need to be, or perhaps a school system might decide to take an action. So that lead time really uh, is determined, of course, by the science and in which time frame we can provide useful information, but then also the decision maker.
Okay, thank you so much. And while we were talking, a whole slew of questions came in, so we're going to get to those. First one is why use MPAS and not FV3?
Okay, so back in 2016, I want to say, is when we started looking at FV3 as a new dynamic core. So that one was selected for NOAA to work with directly, and the RFS, which was developed by GSL, has also gone down the path of using FV3. And what we found was that there were a lot of issues with the representation of updrafts and also precipitation outcomes, like very, very strong updrafts that were not physically realistic. And as a result of that, um, we were not able to emulate the performance that we've seen with our WRF-based WAFs using FV3. And the RFS first version is going to be FV3 based, but both GSL and NSSL are moving to the MPAS focus because that particular system does better representation of convection. And we're really excited to work with its initial developers at NCAR to take full advantage of that.
Thank you. So we're gonna ask a series of questions all together on fire weather. Is the FUFs also used in fire weather applications? And then, do you see it being utilized for hazards like smoke?
Yes. Yes, so I did. I ended up not including a slide on that, although initially I was going to. So I'm so glad that was asked. So yeah, we have developed what we call WAF smoke, and so WAF smoke, it's essentially just another output from Warn on Forecast, which is again taking advantage of satellite information that's really critical for identifying where a fire might be and producing output showing the essentially the density of the smoke, um, the location, and also the movement of the smoke. And so there's been several examples where the WAF smoke part of the system has been able to represent the the smoke plumes and their intensity, the probability of the intensity of those in terms of smoke production quite well. And it's very much like her smoke, only again, taking advantage of some additional satellite information and the rapid data assimilation cycling. And it has been used operationally, I think, by the WFO Norman at a minimum, and I think perhaps also in conjunction with Oklahoma Forestry Services.
Awesome. I'm so glad you mentioned the her because for those uninitiated, could you clarify the difference between the WAFs and the her?
Yeah, so I had a slide on that earlier at the beginning of the talk. Um, but some of the key things are the ingestion of more satellite fields into our data assimilation. The microphysics scheme is different. And then also the cycling with our system is different. So cycling every 15 minutes with output every 5. And we also generate, the model every half hour to top of hour out to 3 hours and 6 hours.
It sounds like someone's eyes are on that all the time then. Okay. Um, we have a few more questions here. Or will slash does the WAFs use atmospheric composition information for the microphysics of storms? For example, aerosol optical depth from GOES.
I would leave that one to someone else to answer. I'm not 100% sure.
Sounds good. We can table that one and get back to you, Joel. And this one touches back on your paper and on WAFs itself. As the initial stages of transition to operations have begun, what resources have been helpful? Where may additional resources help accelerate the transition?
Okay, yes. So We have worked very closely with our NWS partners in the development of a transition plan and getting that approved. And a lot of that along the way, was really from us being able to work with forecasters and be able to demonstrate an experimentally the utility. And so over time, we've been able to increase the number of runs due to support, for example, from the Storm Prediction Center. And then once we got to the point of approval from the National Weather Service, OSTI, they provided funds for us to actually transition our technology to them for them to run on Azure Cloud Services. So that funding was really critical to getting the entire system up and running. They've also put money into us conducting more runs, as well as being able to fund the runs that they're doing. And we are continuing to work with them and other NWS partners to continue forward on other milestones, like training milestones, for example.
Awesome, thank you. And we did have one question that I think you may have addressed already, but I'm just going to bring it up in case there's clarification to be had. Uh, the average tornado warning lead time has been about 10 minutes, falling short of the 13-minute goal. And does WAFs have the potential to increase lead time in the future? And I believe you said there's about an hour now that they could give or possible.
There have been I don't know if there have been. I'm trying to think here. I know that we've provided information to the Weather Service that they have used to put out graphics, showing the very strong potential for tornadoes and other things like that, up to an hour to a couple hours in advance. In terms of increasing lead time, I think there are situations when warn on forecast could be used in that way. However, we also have a product that we call probabilistic hazard information, which was also developed at the lab and with our CIRO collaborators. And that is more focused on producing information, kind of probabilities that are more directly on the warning time scale. And so I think, that information is showing promise for enhancing lead time. And then we've also taken that information and blended it with some of the output from Warn on Forecast to, see where are the sweet spots, for both technologies to come together and also help forecasters do their jobs and, get information out as soon as they can. And, really a lot of that is based on confidence in and trust, in what they are seeing in the model output. Okay, is information available to the public? Yes.
Oh, yes,
Okay.
yes.
Yes, it is. And so I shared our website, but there's also a National Weather Service website that I looked up earlier today. I
Yeah,
think I
Pam, if
can.
you want to drop that into the speaker chat for me, I can grab it and move it over to the audience.
Yes, I just have to look it up real quick because I know when you go to hours, I think it gives you. Oh no, so give me the option. Mhm.
Well, I can definitely share the Warn on Forecast page from NSSL in the chat right now.
Okay, yeah, do that. It's very similar to our cbwops.nssl.noaa.gov,
Okay.
but I don't remember the specifics, but
Mhm.
that web page is being shown by Weather Service, when it is up and running. And our page, you can go back and look at cases from the past several years if you are interested in doing so.
Awesome. Thank you. Let's see. Do we have any more questions? I am not seeing more questions at this time, which is a-okay. Thank you so much, Pam. This has been awesome, and I'm excited to see where this goes next. Oh, Alex put it in the chat for us. Thank you so much, Alex, for that CB WAFs page.
Awesome.
Okay. If there are no other questions, Pam, do you have any last words for our audience today?
Thank you for attending today. And again, I want to thank everyone who was a co author on this paper, the Warren Forecast System from Vision to Reality. This has been such an important team effort, and it will continue moving forward. And thank you, Katie, so much for the opportunity to present today.
Of course. Thank you so much. Thank you, everyone, for joining us for the OAR 2025 Outstanding Scientific Paper Library Seminar Series. I hope we continue these as we celebrate more outstanding papers as the years roll on. Thank you all for joining us. I hope you have a safe, wonderful rest of your day. Thank you.